Look at a perfectly still lake reflecting a mountain, and then compare it to a rough wooden wall. Both surfaces are reflecting light into your eyes right now, but only one produces a crystal clear image. Light is a form of energy. It radiates from primary luminous sources like the sun, bright LED screens, and the bulbs overhead. But most things in the world, like that wooden wall, do not produce their own light. We only see these opaque objects because they intercept light from a source and bounce it directly into our eyes. If human sight is entirely dependent on this bouncing light, there must be a mechanical rule governing the bounce. Something physical dictates whether a surface operates as a flawless mirror or a blank, non-reflective wall. Human vision requires the active decoding of the specific, geometric way light interacts with the textures of the physical world. This animated diagram demonstrates the basic mechanics of reflection. When you throw a ball at the floor, the exact angle of your throw dictates the angle of the bounce. Throw it steeply, and it bounces steeply. Light behaves in a strictly similar manner. A thin beam of light, called a ray, travels in a straight line until it strikes an impassable medium. When it hits that boundary and changes direction, we call the resulting ricochet reflection. We can map the anatomy of this collision. The incoming beam is the incident ray, and the exact coordinate where it strikes the surface is the point of incidence. To measure the bounce accurately, we draw an invisible reference guide. This dashed line is the normal, a perfectly perpendicular line drawn at exactly a 90-degree angle straight up from the point of incidence. The outgoing beam is the reflected ray. By measuring the angle between the incident ray and the normal and comparing it to the angle between the reflected ray and the normal, we discover the fixed mathematical relationship of light. The angle of incidence exactly equals the angle of reflection. Furthermore, the incident ray, the normal, and the reflected ray all exist flatly on the exact same two-dimensional plane. This relationship is so rigid that the path of light is entirely reversible. If a ray travels perfectly down the normal line at a 0-degree angle, it reflects straight back along its exact same path. By identifying these specific lines and angles, we can mathematically predict precisely where a beam of light will travel after hitting any smooth surface. The first law of reflection: the angle of incidence exactly equals the angle of reflection. Light is also completely reversible. The second law locks the incident ray, the normal, and the reflected ray together on a single flat plane. Light operates under a strict set of geometric laws. It behaves like a precise mathematical equation locked to a flat grid. Let's test these laws. On this paper plane, we place a mirror over a normal line. We plot an incident ray with 2 pins at exactly 30 degrees. We then place 2 new pins aligned with the reflection, tracing the reflected light's path. Based on the laws we just established, what will the exact angle of this newly created reflected line be? It measures exactly 30 degrees. The physical reality perfectly matches the incident angle, proving that these mathematical laws allow us to map the invisible path of light. Geometric laws of reflection are unbreakable across the universe. We have to ask why our lake forms a crystal clear image while the wooden wall does not. This animated diagram illustrates what happens when millions of parallel light rays strike a flawlessly smooth surface. They reflect outward together, remaining perfectly parallel to one another. We call this regular reflection. Because these reflected rays remain tightly organized and concentrated, they preserve the visual information of whatever emitted them. This concentrated return of light causes glare and forms the clear images you see in mirrors or still water. Now look at this diagram of a rough surface. Everyday objects like paper or wood are not flat. Microscopically, they are jagged, uneven, mountainous terrains. When parallel rays drop onto this rough terrain, the law of reflection does not break. Every single ray still perfectly mirrors its incoming angle relative to its specific microscopic point of impact. But because the surface bumps face thousands of different directions, the tiny perpendicular normals point in thousands of different directions, sending the rays scattering chaotically. This process is called diffused reflection. Every non-luminous object you see is only visible because of this scattered light hitting your eyes. It leaves us with a question. Are we ever truly seeing the object itself, or just a constructed map of scattered photons?